Hey guys, here's an example where we go a little bit further. We're going to be able to find local max and local min just like before, but we're going to be able to take it one step further and start talking about concavity. Okay? So in order to do concavity, we need to actually look at the second derivative. All right, so let's obviously get our first derivative. Let's just do the stuff we already know now. So 12x squared minus 24x. So that's 12x x minus 2. So I have critical numbers at 0 and at x equals 2, okay? And you would just do your normal routine, no big deal. This is what we did in the other videos. There's your f prime, negative a billion, negative negative is positive, positive 1, we're at positive negative, so that's negative, and then positive a billion is positive positive. So right off the bat, we instantly know our function's increasing, then decreasing, then increasing, and we have a local max at 0, 0 it looks like. And this is going to be 0, 0, and this is going to be 2, oh boy, 32 minus 48, negative 16. So we have a local max and a local min. So same reasoning as before. I'm just going to kind of skip over that part, but I just want to have this handy so we can refer back to it. So this tells me a lot of information. I know where the graph is increasing or decreasing. I know where my local max and local mins are, and I can go from there. But there's another sort of descriptor to kind of help you understand what the graph is doing, and that's called concavity. And concavity lives, concavity lives in the second derivative. So we're going to basically do all the kinds of analysis that we did in the first one with our first layer, but we're going to do it again here, and that's going to tell us about concavity, plus some other things. So let's get our second derivative. So that's going to be, I'll do it here, it's easier, 24x minus 24. Let's get our critical numbers. In this case, there's only one, so I have a critical number at x equals 1. When I go to do my number line for f double prime, that's going to tell me not where the original graph is increasing or decreasing. It's really going to tell me where f prime is increasing or decreasing, and that's concavity. Okay, so if I were to do my number line here, like negative a billion, I get negative, of course, and then positive a billion, I get positive. This is telling me that the graph is concave down up until 1 and then concave up beyond. So in the first derivative, the positive value gave us that the function was increasing. In the second derivative, a positive value tells me that I have concave up. When I have negative in the first derivative, that's decreasing for the function, and this is the function having a concave down sort of visual from this point to this point. Okay? So what I would say is f of x is concave down on negative infinity to 1 because, and it's very similar, f double prime is less than 0. This is the concavity test. So it's exactly like the increasing decreasing test, but you're just on the second derivative level instead of the first derivative. And all this information is telling us about the original function. The whole point of doing all this stuff is to learn about how this original, actually looks, what this graph looks like. So we can get a max, we can get min, we can get increasing, decreasing, we can get whether it opens down or opens up, right? Concave down, concave up. So that's going to help us actually get the graph. F of x is going to be concave up on 1 to positive infinity because f double prime is greater than 0. And at this point, I don't have a local max or local min, not on the original function. You could say you have a local max or a local min on the derivative if you want, but that's not really as useful. So what we call this, where the concavity changes, right, from negative to positive or positive to negative, we call that a point of inflection. So f of x has a point of inflection, and I'm just quoting it because that's something you'll see often, a point of inflection at 1 comma, let's see, where am I, negative 8, 1 comma negative 8, because, and the only thing that has to happen here is you have to have concavity changing sign, and of course the value has to be defined. If you go to plug 1 back into the original and all of a sudden this is undefined, well then it's certainly not a point of inflection if it's not even a point on the graph. But this one's definitely on the graph. So f has a point of inflection at that point because f double prime changes from negative to positive. And you could simply say it changes sign. That's pretty obvious for that one. The reason why we have to get more specific when we do max and min is because those are two different things. This is just simply a point of inflection. There's no, max point of inflection or min point of inflection. You just say point of inflection. Okay? I think that should take care of a pretty good, that's a pretty good example of finding concavity and finding the point of inflection. But I'll do another one, but hopefully this will help. And if you need anything else, you just let me know, and I will talk to you guys later.